Okay, after we studied the F-test for joint hypothesis for multiple regressions, let's look at the potential misspecification problem and the collinearity or multicollinearity for multiple regression models. Okay, so first, let's look into misspecification. There can be two kinds of model misspecification. Okay, one is called omitted relevant variables or omitted variables. So omitted variable problem happens when you don't include a variable that's actually influence y in your model, and that's also correlated with the variables you already included in the model. Okay, and the second type of model misspecification is called including irrelevant variables. And in this case, you include a variable that doesn't help you to explain the movement of the dependent variable. And in this case, it generally doesn't help the fitness of the model, but at the same time, it may lead to larger variance of your estimators. Let's just try to take a look at an example of this case. Okay, so first, let's look at the model we discussed in the previous sections. Let's just look at this model where we try to explain the movement of housing prices using a constant term, the square foot of the house, and the number of bedrooms of the house. Okay, our results show that beta 2 is significantly different from 0 in this model, while beta 3 is not. So what does it mean? Just coming back to how we explain the coefficients in the multiple regression, you should know that this means basically when there's a change in the square foot of the house, that will lead to a change of the housing price, holding the number of bedrooms equal, okay, for holding the number of bedrooms unchanged. Well, if there's a change in the number of bedrooms in your house, where holding the square foot unchanged, it doesn't have any impact on the housing price. So basically, in this case, you can loosely say that square foot is kind of a useful variable in explaining housing price, while number of bedrooms is not so useful in explaining the movement of housing price. Okay? And when you do this regression, you can also say that suppose you do the regression as log of housing price is equal to alpha plus alpha 1 plus alpha 2 times number of bedrooms, then you are faced with a problem. Your model suffers from the problem of omitted variables, which means that you included a not so useful variable, but you didn't include a very useful variable. And also in this case, you're going to see in a moment that when you do this regression alone, you're actually going to see a significant coefficient for the number of bedrooms, but actually that is not right. That is not right, okay? And also when we know that when beta 3 is not significant, then you could also say that suppose we go from a model where we only include the square foot of the house as the independent variable to the model that also includes the number of bedrooms, we can say that you're including an irrelevant variable in the bigger model. You're including a kind of irrelevant variable in the bigger model. All right, so let's take a closer look at the problem of omitted variables, okay? So if we just look at the case where you regress the log of housing price on the constant and number of bedrooms, so in general, you're going to see a significant alpha 2. And that will lead you to think that if you increase the number of bedrooms, that generally leads to a higher housing price, okay? But the truth is, it's not a case that when you have more bedrooms, it's going to increase your housing price. The true story is houses with more bedrooms are typically larger, okay? So they are more expensive because they are larger, all right? And when the area is controlled, increasing the number of bedrooms usually do not lead to increase of the housing price. Okay, so if you do not include, if you omit the true useful variable of the area, or if you omit the variable true useful variable of square foot, you will reach the wrong conclusion that holding other things unchanged, more bedrooms lead to higher price. Okay, so indeed, there is a positive correlation between number of bedrooms and the housing price. But once you know the true model, you should understand that this positive correlation is not causality. Okay, so houses with more bedrooms are more expensive, not because they have holding other things the same, they have more bedrooms, but because they are just bigger. All right. Okay, so if you use the wrong model with the problem of omitted variables, that could make people think that, okay, suppose you make segregation in your master bedroom and make it into 2 small rooms, then it will increase the housing, the price of the apartment. But that's actually definitely not true. That's definitely not true. Okay. All right. So from this story, you can see that the omitted variable problem will be more problematic if the omitted variable is correlated with the existing independent variable in the model. Okay, and it could also lead to a bias estimator. So in this case, we can clearly see that when the true causal relationship is from square foot, from the area to the price, but if you don't include the true useful coefficient, true useful variable, but use a wrong variable, you're also going to see a significant coefficient, but it's a bias estimator and give you the wrong information. Okay, so and in this case, actually, we also understand that if the omitted variable is uncorrelated with any of the independent variables included, it generally causes less a problem. Okay, so that's the problem of omitted variable. And also you can see that if you go from the bigger model to a small model, let's say if you drop the irrelevant variable of number of bedrooms, okay, so you will see that in general, the model should give you a better significance of the useful variable. Okay, so that's for the irrelevant variable. But usually, if you do a model estimation for empirical data and also for your paper, irrelevant variable is not as big a problem as omitted variable. So in this course and also in your paper, we usually pay more attention to the problem of omitted variables instead of irrelevant variables. Okay, and the next step is that we want to study how to detect the problem of omitted variables. So once we know that omitted variable is a big problem, it leads to bias estimators, then we should be able to think of a way to test for it. Okay, so if we want to test for omitted variables, the method recommended by the textbook is to conduct something called Ramsey reset test. Ramsey reset test. Okay, so this is basically how the Ramsey reset test works. Okay, suppose you have a model. Y is equal to beta 1 plus beta 2x plus beta 3x3 plus e. Okay, so after you run the regression, you can first generate the fitted value of y by doing y hat is equal to b1 plus b2x2 plus b3x3. And then what do you do? So then you run a so-called auxiliary regression. You run another regression where you also include the square of the fitted y as an independent variable of your auxiliary regression. And after you run this auxiliary regression, you do a t-test on the coefficient of gamma 1, whether it's the null hypothesis is gamma 1 is equal to 0, and the alternative hypothesis is gamma 1 is not 0. And if you reject the null hypothesis of gamma 1 equal to 0 in favor of gamma 1 is significantly different from 0, then that's a suggestion you might have the problem of omitted variables. Okay, so why is that the case? The intuition behind the Ramsey reset test is the following. Okay, so suppose there is some omitted variables that's correlated to x2 and x3. Okay, so then they must be also correlated to x2 squared, x3 squared, or x2, x3, the product of x2 and x3. Okay, so then suppose the original form of the estimation is incorrect, and there is a variable that influences y that's not included in the model, but correlated with x2 and x3. They should also be correlated to these guys. And if so, if you include the square of the fitted y, you will see that since y, the expression of fitted y is like this. So basically, by include the term of square term of fitted y, you're also including the square term of x2, or the square of x3, and the square of x2 and x3. So basically, if there is no omitted variable, then the coefficient for x2, so y hat squared, shouldn't be significant. And if there is indeed a kind of omitted variable that's correlated to all those guys, the square term of x2 and 3, or the product of x2 and x3, so then if those coefficients are significant, that should also lead to a significant coefficient for y hat squared. So basically, in this case, once you see that gamma 1 is significantly different from 0, then that's an indication that the square term of x2 or x3, or the product of them, they are also significant. So then there's a problem, an omitted variable to the regression. Okay. All right. And if you want to do reset tests in eViews, this is how you can do it. Again, just after you run the regression, when you see the output table of the regression, you can go for the button View, Stability Test, and then you go for Ramsey Reset Test. Okay, and when you click the Ramsey Reset Test, usually they will ask you to select the number of fitted terms. Okay, so basically you can select it to the second power, third power, fourth power, so on and so forth. Okay, and after you do that, so usually we can just select up to power 2 or power 3. That's quite sufficient. And after you select that, they will just report for you the p-value of the test. And remember, the null hypothesis of Ramsey reset is that there is no omitted variable. And if you see a p-value that is less than 0.05, then that will be a suggestion of rejecting the null of no omitted variables, and that's something in favor of that you have omitted variable problem for your regression. Okay, so that is for the reset test for omitted variables. After we discuss the omitted variables, we can also visit the other potential problem that is called collinearity or multi-collinearity. Okay, so just to recall that when we studied the chapter at the beginning, right, when you have a multiple regression and suppose you have a fitted value of the regression, you have the estimators B1, B2, and B3, right? So the variance of any coefficient, like variance of B2, should be equal to this, and where R23 is the correlation between x2 and x3. In this case, you should know that when R23, namely the correlation between x2 and x3, is close to 1, this term here, 1 minus the square of R23 squared, should be very close to 0. And when this happens, you will see that the whole term will be very close to infinity. So something divided by 0 is close to infinity or undefined. And in this case, if you do that in eViews, usually eViews will just say that I cannot do it for you. So it's a kind of a singularity matrix. I think that's probably the error report they say. Okay, so basically when the x variables are too closely related, it generally leads to very noisy estimation or even impossibility of estimation. Okay, so and when this happens, suppose we have a perfect correlation, perfect relationship between x2 and x3, we say that the regression suffers from the problem of multi-collinearity. Okay, All right. So then how can we detect the problem of multicollinearity? So basically, there are two ways. Both of them are not so hard, okay? So first of all, what you can do is you can simply, in eViews, you can simply click on two variables, open them as a group, and look at the correlation matrix or correlation coefficients. If you see that the correlation between x2 and x3 are 0.8 or more, or 0.9 or more, that's usually an indication of multicollinearity. And in that case, it's not so good to include both x2 and x3 in your regression, okay? And the second possibility, the second way you can do it is you just regress one of the x coefficients on all the rest of the x variables, and you can do it for all the independent variable x's, as long as you see one of the regressions has a R-squared that is very high, namely larger than 0.8, then in general, it means that one of the variables, independent variables, is too closely related to the other variables, and in this case, you might also have the problem of multicollinearity.